Welcome to Digital Control Systems Practical. Today we are studying Lab 8, which is based on the design of PI controllers using bilinear transformation. The basic learning objective of this lab is to analyze the open and closed loop response of this system. Second part covers the design of the PI controllers to meet the given design specifications. There are two types of control systems. The first one is open loop system, also known as the without feedback control system. In open loop system, we gave the input to the controller process and gives the output. Provide no feedback signal. Closed loop systems are those systems in which the feedback loop is present. We gave the input to the controller process. If get any error, then it send the feedback to the controller and repeat all the process again and get the accurate output. That's why closed loop systems are also known as the accurate control systems, in which the accuracy part is much better and much reliable as compared to the open loop system. Open loop systems in which the optimization portion is not available, but in closed loop system optimization is available, and open loop systems are less reliable and less accurate as compared to the closed loop system. That's why in our practical life mostly we use the closed loop system. Example of open loop system is water heater, and closed loop system example is the electric AC. We have already studied the PID controller in detail in linear control systems lab. Here I am giving you the overview of the PID controller. PID stands for proportional, integral and derivative controller. P itself a controller, I itself a controller and D itself a controller. Each controller performs different functions. In our practical life, we are using the combination of these controllers. We mostly use the PI and PD controller combination. Here in this lab, we are using the PID controller. If you want to decrease the steady state error, increase the control system response. So we use the integral controller. The basic advantage of this integral controller is it will improve the response of the control system by decreasing the steady state error, but also affects the stability of the system. That's why we combine the integral controller with the proportional controller. So by combining this integral controller with the proportional controller, by using this combination, we are improve the response of the control system by decreasing the steady state error, but also without affecting the stability of the system. The major advantage of this combination is that we are not affecting the stability of the control system. Basically, in our control system, stability is most important part. That's why we are using the combination of these controllers to overcome these problems. This controller must be proportional to the error and also must be proportional to the integral of the error signal. Bilinear transformation is basically a method for converting the continuous system into a discrete system. The bilinear transformation is used in digital signal processing and discrete time control theory to transform the continuous time system representation to discrete time. Basically, we can get the data in a continuous form and also convert into discrete form by using different methods. In today's lab, we are using the bilinear transformation method to perform this operation. How to design a digital controller. There are different methods to design the digital controller. In this lab, we are trying to obtain an equivalent digital controller by using the bilinear transformation method, in which we take the continuous time control system and then we digitized it using zero order hold operation. The first block diagram is for the continuous time control system, in which the R of S is the input or the reference signal, E of S is the error signal, and the D of S block is basically for the PI controller, and U of S is the control signal, and G of S is the plant transfer function, and Y of S is the output. And then we discretize this continuous time system by using the zero order hold operation. The second block diagram, in which the R of S and then T and then D of Z is basically the PI controller in discrete time. And then we are using the ZOH operation, and G of S is the plant transfer function and Y of S is the output. This design works very well if we are using the efficient sampling time period, which is T. And similarly one could discretize the plant first to obtain a sample data system or discrete time system, and then apply the digital control system technique to design our digital controller. This is the final block diagram after implementing the technique. And in this block diagram, the controller, PI controller, and the plant transfer function in a discrete form is present. And in our MATLAB code, we are implementing this block diagram. Today we are perform this example on MATLAB Simulink. Consider a car which has a weight n equals to 1000 kg. Assuming the average friction coefficient B equals to 100, design a QoS control system, basically also known as the speed control system, such that the car can reach 100 km per hour from 0 km per hour in 8 seconds with an overshoot less than 20%. This is the block diagram for this example. This block diagram shows that this is a continuous time control system. Let us try a PI controller. ds equals to kp plus ki over s. The first component is proportional to the error, and the second consists of an integral action. And here is the transfer function for this block diagram. And transfer function is basically equals to the ratio of the output over input. And after putting these values, we can get the transfer function, which is equals to 0.001 kp s plus 0.001 ki over s square plus 0.1 plus 0.001 kp s plus 0.001 ki. This is the second order. After solving the transfer function equation, we get the kp and ki values. Kp equals to 1050 and ki equals to 670. Here is the Simulink model of continuous time system. We get these blocks from a Simulink library browser. The first block is the step signal and the second is the submission. By double clicking on the submission icon, we can change the symbol plus plus. Basically, when pick this submission icon, plus plus icons, basically plus plus symbols are shown, but now we can change the symbol by double clicking on this icon, and then we pick the PID controller by double clicking on this block. We select the first we select the PI controller, and then we can put the nominator and denominator values, and then we pick the transfer function block, and the transfer function block, which is basically rewrite here is its name we can rewrite, and then the transfer function block is placed, and then we put the numerator and denominator values, and then we pick the scope block. Here, by clicking the after running this model, by double clicking on this scope block, we can see our output. This is the output of the continuous time control system, and the straight line and the constant line shows that the constant steady state response for this system. Discretization of the controller using bilinear transformation. First, we discretize the continuous time PI controller with sampling time period, which is approximately equals to 0.1 second, using a bilinear transformation method. In bilinear transformation method, S equals to 2 divided by T z minus 1 over z plus 1. We can make a digital controller. We solve this equation, and D of S is basically the PI controller or controller in continuous time. And by solving this equation, we can get the digital controller value, which is equals to 108.5 z minus 1016.5 over z minus 1. We can also write this z minus 1 into z minus 1 equals to z inverse. This Simulink model is for the design digital controller. First, we click on the Simulink option on the status bar, and then we open the Simulink library browser. From Simulink library browser, we pick all these blocks. First, we take the step block and place on the blank model. By double clicking on this step block, we can define its initial final value. Here we put the final value is 100, and then we pick the submission block, and also double click on this block and change the symbols plus minus. And after this, we take the digital controller, basically discrete time controller. Discrete time controller, take the discrete time controller and place this block on and place this block, and also double clicking on this block, we define the numerator and denominator values. After this, we can pick the ZOH block from the discrete time, and then we pick the transfer function block and rewrite its name plant, and also define its numerator and denominator values by double clicking on this block. And at the very last, we take the scope block for uh, scope block for output. and then we gave the feedback to the submission. This is the output of the digital controller using the bilinear transformation method, and we discuss this digital controller response in a live session according to the timetable. In live session, here is the lab task, in which assume that the model of the DC motor is represented by the following transfer function: G of S equals to omega m over S over V A S equals to K of m over tau of m S plus 1, where K of m equals to 1 and the tau of m equals to 5. By putting these values, you can get the G of S equals to 1 divided by 5S plus 1. And then design the continuous time PI controller to meet the following design specification. For this point, you can follow the slide number 11, where the continuous time control system Simulink model is present. You can follow this Simulink model for this step. The percentage overshoot of the closed loop system should be less than 10%, and settling time of the closed loop system should be less than 1 second. Steady state error should be 0. You can use this transfer function for the designing of digital controller. This is the second part of your lab task. When we are coming the next week, before starting the next lab, I will ask some questions from the previous lab, and also I will check your lab tasks first. If you have any query regarding the lab 8 and also regarding the lab task, you can freely contact me on Microsoft Teams.